The longest winter in the solar system, Mars did not freeze all at once. It entered a winter that never truly ended, a slow descent into cold that reshaped the planet more thoroughly than any impact ever could. This was not the dramatic freeze of catastrophe, but the gradual cooling of decline, a transition so incremental that no single moment marked the passage from warm to cold, from seasonal to permanent, from temporary to eternal. Mars's longest winter was not an event but a process, one that transformed every aspect of the planet's climate, geology, and potential for life over billions of years. To understand why this matters today, we have to stop thinking of winter as a season. On Mars, winter became a condition. As the atmosphere thinned and heat escaped more easily, cold stopped being temporary. It became permanent. And permanence changes everything. Winter on Earth is endurable because it is transient. Spring always follows, warmth returns, ice melts, and life resumes. But when winter persists indefinitely, when the seasonal cycle breaks and never recovers, the planet fundamentally transforms. What begins as cold weather becomes cold climate, and cold climate eventually becomes cold identity. Mars did not experience winter. It became winter. Early Mars experienced seasons much like Earth. Temperatures shifted, ice advanced and retreated, water moved between states. But as atmospheric pressure dropped, that balance began to fail. Each winter lasted longer than the last. Each thaw returned less than before. Evidence suggests early Mars had seasons driven by axial tilt and orbital variations, just as Earth does. During warmer periods, ice at the poles would sublime or melt, releasing carbon dioxide into the atmosphere and creating a modest greenhouse effect that maintained relatively moderate temperatures. During colder periods, this carbon dioxide would refreeze at the poles, thinning the atmosphere but not catastrophically. The cycle was stable because enough atmosphere remained to buffer the extremes. But as atmospheric loss progressed, this buffer eroded and the seasonal cycle began to fail. Carbon dioxide, once cycling between air and ice, began locking itself at the poles. With less gas in the atmosphere, heat retention weakened further. Cooling accelerated. Mars entered a feedback loop, where cold created more cold. Each winter's freeze sequestered atmospheric carbon dioxide as dry ice at the poles. If the subsequent summer was not warm enough to release all of it back into the atmosphere, the permanent ice caps grew slightly. This incremental growth over millions of cycles gradually removed carbon dioxide from active circulation, thinning the atmosphere and reducing its greenhouse capacity. Less atmosphere meant less heat retention, which meant colder temperatures, which meant more carbon dioxide freezing out, which meant even less atmosphere. The feedback was positive. Each change reinforced and amplified itself, driving Mars inexorably towards frozen state. Over millions of years, this process transformed the planet. Glaciers carved valleys that never melted. Ice became trapped underground, unreachable. Any remaining surface water disappeared entirely. Mars crossed from cold to frozen. The transition was not abrupt but gradual, spanning perhaps hundreds of millions of years as the planet slowly cooled. Glaciers advanced across the surface, sculpting features that would be preserved for billions of years. As surface ice sublimated or was buried under dust, subsurface ice formed extensive deposits that remain frozen to this day. The transition from a world with liquid water to one with only ice was complete. Mars became a frozen desert, where temperatures rarely rise above freezing and surface ice is stable only in the coldest regions. This was not a dramatic collapse. It was endurance in reverse, a planet losing energy year after year until warmth became impossible to sustain. Mars did not survive its longest winter. It adapted to it by becoming something else. Rather than catastrophic transformation, Mars underwent steady degradation, where each year was marginally colder than average, each decade slightly more frozen, each millennium measurably more hostile. The changes were imperceptible on human timescales, but profound over geological ones. Mars adapted by ceasing to be the planet it once was, and becoming instead the frozen world we observe today. And that endless cold still defines Mars today, not as a temporary state, but as the final shape of its climate. Mars is not waiting for spring. It has already lived through winter without end. The cold is not a phase, but the conclusion, not a condition but the identity. Understanding this permanence is crucial for any assessment of Mars's current state and future possibilities. The cold will not end through any natural process. It is the equilibrium state that Mars has reached after billions of years of atmospheric and thermal evolution. As Mars cooled, winter stopped being a season and became a planetary process. Each cycle of freezing pulled more gas from the atmosphere and locked it away as ice. What remained above the surface grew thinner, weaker, less capable of holding heat. The atmosphere-ice interchange that once maintained balance became unbalanced, with net transport from atmosphere to ice caps. This one-way flow progressively depleted the active atmosphere, removing the thermal blanket that had moderated temperatures. As the atmosphere thinned, its capacity to distribute heat from equator to poles and from day to night diminished. Temperature variations increased. Extremes intensified. The climate lost its moderating mechanisms. Unlike Earth, Mars had no oceans to store warmth, no tectonic activity to recycle carbon back into the air. Once gases froze or escaped, they were effectively gone. The climate system lost flexibility. Variability collapsed into monotony. Earth's vast oceans act as thermal reservoirs, absorbing heat during summer and releasing it during winter, damping seasonal extremes. Plate tectonics continuously recycles carbon between rocks, atmosphere, and ocean, maintaining long-term carbon balance. Mars had neither system. No ocean to buffer temperature swings. No tectonic recycling to replenish atmospheric carbon dioxide. The climate system became rigid, unable to self-correct when pushed toward extremes. Once carbon dioxide froze at the poles, it remained there indefinitely, never returned to warm the atmosphere. Ice expanded across vast regions. Some glaciers flowed slowly, carving channels that would never see liquid water again. Others became buried beneath dust, preserved like fossils beneath the surface. Mars accumulated cold the way Earth accumulates heat, gradually and relentlessly. Glacial features visible today record the advance of ice across regions where warmer conditions once prevailed. Valley glaciers carved distinctive U-shaped cross-sections. Continental ice sheets smoothed highlands and deposited till. As the climate continued cooling, these glaciers ceased to flow, freezing in place and often becoming buried under accumulating dust. The subsurface ice deposits discovered by orbital radar and lander instruments represent these ancient glaciers, preserved beneath protective layers of regolith, frozen memorials to Mars's descent into permanent cold. As temperatures dropped, chemical reactions slowed, weather weakened, storms lost energy. The planet's ability to redistribute heat failed. Mars became locked into extremes, with brief summers unable to undo the damage of long winters. Temperature affects chemical reaction rates exponentially. Small temperature drops produce large reductions in chemical activity. As Mars cooled, weathering slowed, mineral formation changed, and surface chemistry effectively froze into patterns determined by ancient conditions. Atmospheric dynamics weakened as the temperature gradients that drive circulation diminished. Storms, though still occurring, became less effective at transporting heat. The climate developed steep thermal contrast between sunlit and shadowed regions, warm and cold latitudes, that persisted because circulation could not equilibrate them. Summers briefly warmed surfaces but could not penetrate the frozen subsurface or significantly warm the deep atmosphere. This transition also altered the planet's surface chemistry. Frozen ground cracked and fractured. Minerals formed under conditions that no longer exist. Mars's geology became a record of cold rather than motion. Freeze-thaw cycles created polygonal fracture patterns visible at all scales. Minerals that form only in the presence of liquid water became relics of a warmer past, surrounded by minerals that form under frozen, arid conditions. The geological record transitioned from signatures of activity and fluidity to signatures of stasis and permanence. Mars's rocks chronicle not ongoing processes, but completed transformations, preserving evidence of the longest winter written in mineralogy, texture, and structure. What makes this phase so important is its finality. Once Mars entered its longest winter, there was no mechanism to escape it. The processes that could have restored warmth were already gone. Volcanic outgassing, which might replenish the atmosphere, had largely ceased as the planet's interior cooled. Asteroid and comet impacts, which might have delivered volatile materials, were insufficient to reverse billions of years of atmospheric loss. Solar luminosity was fixed. The sun could not suddenly burn brighter to warm Mars. With no internal or external force incapable of re-warming the planet, the cold became permanent. Mars had crossed an irreversible threshold. Mars did not freeze because it was far from the sun. It froze because it could no longer keep what little heat it had. And that loss turned time itself into an agent of cold. Mars's orbital distance from the sun places it within the potentially habitable zone where liquid water could exist with sufficient atmospheric pressure. The freeze resulted not from insufficient solar energy, but from insufficient atmospheric capacity to retain that energy. Every day the sun warmed Mars's surface, and every night that warmth radiated away into space without being trapped by a thick atmosphere. The cumulative effect of billions of such cycles was progressive cooling. Time did not heal Mars or restore balance. It deepened the cold, each passing year locking the planet more firmly into its frozen state. The conflict of Mars's endless winter lies in how gradual it was. There was no moment when the planet crossed from warm to frozen in a single step. Instead, each winter stole a little more than the last, until recovery quietly slipped out of reach. This gradualism makes the transition difficult to conceptualize. There was no catastrophic freeze, no ice age that suddenly consumed the planet. Instead, there were countless small losses, a slightly thinner atmosphere this millennium, marginally colder average temperatures next million years, incrementally more carbon dioxide locked in polar ice the following epoch. Each change was small enough to seem survivable, but the cumulative effect was devastating. Mars still received sunlight, it still experienced seasons, but the system no longer responded. Ice advanced faster than it retreated. Atmospheric pressure dropped below critical thresholds. Liquid water could not exist long enough to matter. The planet kept cycling, but the cycles no longer restored balance. This is perhaps the most insidious aspect of the transition. Mars continued to exhibit seasonal behavior even as it fundamentally transformed. Polar ice caps still wax and wane with the seasons. Temperature still varies with latitude and time of day. But these variations occur within a framework that is permanently cold rather than temporarily frozen. The cycles persist as shadows of their former significance, unable to affect meaningful change. This creates a dangerous illusion. From a distance, Mars might appear stable, calm, predictable, but stability built on exhaustion is not resilience. It is stagnation. Mars demonstrates how a system can look settled while actually being locked into failure. The planet has reached equilibrium, but it is the equilibrium of death rather than life, of stasis rather than dynamism. The appearance of stability masks the reality that Mars has exhausted its capacity for change and settled into a permanent condition from which no escape is possible through natural means. The conflict becomes clearer when compared to Earth. Earth's winters end because energy is stored and released. Mars's winters did not end because storage failed. Once energy escaped, nothing replaced it. Earth's oceans, atmosphere, and biosphere all store energy across timescales from diurnal to millennial, allowing the climate to maintain balance despite perturbations. Mars lacked these storage mechanisms. Energy arriving from the sun during the day was not stored for release at night. Energy absorbed during summer was not stored for release in winter. Without buffering, the climate became unstable, responsive to every fluctuation, incapable of maintaining equilibrium. Life, if it persisted at all, would have faced shrinking windows of opportunity. Shorter thaws, deeper freezes, increasing isolation. Adaptation would have required retreat underground, slower metabolism, or extinction. Any organisms existing during Mars's transition into permanent cold would have experienced progressively more hostile conditions. Habitable periods grew shorter and less frequent. Temperatures dropped. Ice advanced. The surface became increasingly inhospitable, forcing life to retreat ever deeper underground or into ever more restricted refuges. For most organisms, adaptation could not keep pace with environmental change. The longest winter was not survivable. It was terminal. Mars did not fight its longest winter. It endured it until endurance itself ran out. And once that happened, the planet crossed into a state where recovery was no longer possible. The conflict was never cold versus warmth. It was time versus resilience. And time won. Mars had finite resilience, finite atmospheric reserves, finite internal heat, finite capacity to buffer change. Time, by contrast, was effectively infinite. Given enough time, every finite resource exhausts. Mars's resilience held for millions of years, delaying the inevitable but never preventing it. Eventually, resilience failed, and time delivered the final outcome: permanent cold. The climax of Mars's longest winter is the realization that it never truly ended. What we see today is not a pause between seasons, but the final outcome of a climate that lost the ability to recover. Mars is not currently experiencing winter, with spring ahead. It is experiencing permanent cold that will persist for the remainder of the solar system's lifetime. This is the end point, the equilibrium state, the conclusion of billions of years of climatic evolution. Once the atmosphere thinned beyond a critical point, warmth became temporary and insignificant. Ice dominated. Energy escaped faster than it could be retained. Mars did not enter winter by accident. It settled into it by inevitability. The transition was deterministic, driven by the planet's physical properties: its size, mass, orbital distance, magnetic field history. Given these parameters, the longest winter was not a possibility, but a certainty. Physics demanded it. Time delivered it. The resolution of this story is written into the planet's stillness. Mars is cold not because it is distant, but because its systems no longer circulate energy. Winter became permanent when balance disappeared. The cold we measure today, average surface temperatures around minus 60 degrees Celsius, with extremes reaching below minus 100 degrees Celsius at the winter poles, represents not a temporary state, but the stable condition Mars will maintain indefinitely. The planet has settled into thermal equilibrium with its environment, an equilibrium that is frozen, barren, and final. Mars teaches a subtle lesson. Collapse does not always arrive as destruction. Sometimes it arrives as permanence, as a state where nothing improves, even though nothing dramatic happens. The planet demonstrates that failure need not be violent or sudden. It can be quiet, gradual, almost peaceful, a gentle slide into a state for which there is no return. This form of collapse is perhaps more unsettling than catastrophic destruction because it is so difficult to recognize and resist while it is happening. The longest winter in the solar system is not measured in years. It is measured in lost options. Mars has no spring ahead of it, only continuity of cold. The duration is not what matters. The permanence is. Mars will remain frozen not for a season or an epoch, but for eternity, or at least until external forces, human terraforming, asteroid impacts, stellar evolution, intervene. The cold has become the permanent state, the defining characteristic, the immutable reality of modern Mars. And that is why Mars matters. It shows what happens when a world loses the ability to change, and time itself becomes a final force shaping everything that remains. Mars is a warning written in ice and stone, demonstrating that planetary habitability is fragile, that climate systems can fail irreversibly, and that gradual decline can be as devastating as catastrophic collapse. The longest winter teaches that some thresholds, once crossed, cannot be recrossed, and that time, given infinite duration, will exhaust any finite resilience. Sometimes the smallest shift in perspective becomes the beginning of a new future. And sometimes that shift is recognizing that permanence can be a form of death, that stability can mask stagnation, and that the longest winters are not those we endure, but those from which we never emerge. The